So how do we find the area under the curve y equals x minus 1, the hyperbola? It was perhaps one of Fermat's contemporaries, Gregory de St. Vincent, who realized that when we use this method, the areas under these rectangles remain equal. So for instance, the base of this rectangle is a minus a to the r times the height a to the negative 1. Written like that. And we can factor out the a, and then we get this. But the a and the a minus 1 here cancels out, and so the area is 1 minus r. And then for the next rectangle, we subtract ar squared from ar multiplied by the height ar negative 1. Okay, and we can factor out the ar, so we got ar times 1 minus r times ar to the negative 1. And of course these cancel out, and the area is again 1 minus r. And the same thing for the next rectangle, ar squared minus ar cubed, right? Multiplied by the height ar squared to the negative 1. Okay, we can factor out the ar squared. And these two cancel out, and we get again 1 minus r. So the area of all these rectangles is 1 minus r. What this means is, as the distance grows geometrically, the corresponding area grows arithmetically. That is, in equal increments, even as r approaches 1. What does that mean? That means that the relationship between the area and the distance is logarithmic. That is, from a fixed point, the area under the hyperbola at point t is log t for some base. And this is one of the first times that logarithms have been written as a function. Before this, logarithms were just seen as tools to make very complicated calculations, So now the question is, what is the base of this log corresponding to the area under the hyperbola?